As we look at the nucleus, because in this particular unit we're looking at atoms, the nucleus is something that baffled scientists for many, many, many years. If we look inside the nucleus, in our previous video we said that they were made up of neutrons, which have no charge, and protons, which have a positive charge. Now, the nuclear force itself, what holds the nucleus together, is one of the strongest forces in nature. But if you look at this and think about charges, that doesn't really make any sense. That is that strong. What scientists find confusing about this is the fact that we have things that are positively charged and things that have no charge at all. Now, if you think about magnets, we know that if we have magnets who approach each other with opposite charges, we know that and we'll use this for relationships, everything else, opposites attract, which means that if I put the positive end of one magnet next to the negative end of another, those two things are going to attract to each other. If I put like charges together, so I have the positive end next to the positive end, this is going to cause the magnets to actually repel. And if I take a magnet and put it up to something that has absolutely no charge, like a piece of wood, then nothing's going to happen at all. There's not going to be attraction, there's not going to be repulsion. So go back and look at my picture of the nucleus. I have positive things touching positive things and positive things touching neutral things. There's nothing negative in there whatsoever. So this makes no sense that the nucleus is held together so tightly and so strongly if you're just simply looking at the overall charges of each particle. Which brings us to what is known as the quark theory. Now, I mentioned at the beginning that there are scientific theories. There are good scientific theories. There are some that are more questionable. And, the quark theory is a really good theory that explains why the nucleus stays together. It also explains where the masses of the neutron and the proton come from. Now, is this true? And anytime you're asked if a scientific theory is true, the answer is maybe. A scientific theory in science itself is tentative. It's subject to change. As we learn things, we change, as we learn new information, it changes what we know about things. Therefore, our theories are subject to change. Now, according to quark theory, there are two basic particles. There are particles known as baryons and particles known as leptons. Now, the two most common baryons, and there are more than these two, but the two most common is what we've already talked about, the proton and the neutron. The two most common leptons are the electron and what is known as a positron, which would be technically an antimatter particle. It's a positively charged electron. Now, baryons are made up of what's referred to as 3 quark combinations. And the two most common quarks are the up quark and the down quark. Protons are made out of 2 up quarks plus 1 down quark. Now, each up quark has a mass of 1/3 of an AMU. There are 2 of them, so we're going to add it twice. Plus the down quark also has a mass of 1/3 of an AMU. When we total this up, we get 3/3, which is 1 AMU. 1 atomic mass unit is what we said that the mass of a proton generally is. Now, if we look at the charge, we said it has 2 up quarks. Each of them has a charge of plus 2/3. Plus the down quark, which has a charge of negative 1/3. Well, 2 plus 2 is 4, minus 1 is 3. Here again we have charge of plus 3/3, which is plus 1. And you know from the introductory atomic video, we said that the charge of a proton is a positive 1. If we look at the neutron, it's made out of 2 down quarks plus 1 up quark. Well, looking at the mass, each down quark has a mass of 1/3 AMU. And the up quark also has a mass of 1/3 AMU, for a total mass of 3/3, which is 1 AMU. Now looking at the charge of these same particles, we said that the charge of a down quark is negative 1/3. There are 2 down quarks in the neutron, therefore each one has the same charge of negative 1/3, plus the charge of the up quark, which is a positive 2/3. Negative 1 plus negative 1 is negative 2, plus a positive 2 is 0/3, which is a charge of 0. We say that neutrons are neutral because their overall charge is 0. So if you look back at our earlier slide regarding the nucleus having, this particular one having 4 protons and 3 neutrons, well, instead of thinking this as being a solid thing that has a solid positive charge, we look at the quarks inside of it, then we see that where the protons having 2 up quarks and 1 down quark, okay, and the neutrons having 2 down quarks and an up quark, you see that there are areas in each one where you have a down quark which has a negative charge touching an up quark which has a positive charge. And you see where it happens here and here, and so forth and so on, where you have a down quark that's attracted to an up quark in an adjacent baryon. Now, even though this has an overall positive charge, and these are neutral because they're neutrons, okay? Or shall I say they are neutrons because they're neutral. You're looking at a positive thing next to a positive thing, but there's a positive area of this proton that is next to a negative area inside of this proton. And this is what the quark theory explains as far as how the nucleus stays together. So here again, it's an excellent theory to help us understand this. Is it true? Maybe, maybe not. As we learn more, we adjust our theories so that they match what we actually observe in nature. Other than just straight up, basic questions about what is a proton made of, what is a neutron made of. There are some limited math questions that could be asked on a quiz or test. Regarding quarks, this would be one example of a question where it asks how many up quarks are contained in one lithium-7 atom. Now, lithium-7, if you look at it in terms of protons and neutrons, lithium's atomic number is 3, therefore it's got 3 protons. Okay? Now, the total mass here is 7, and to get the neutrons, remember we take the mass number, which in this case is 7, and subtract the protons, so 7 minus 3 is 4. So the lithium-7 atom is going to have 3 protons and 4 neutrons. Now each proton is made up of 2 up quarks and 1 down quark. Each neutron is made out of 1 up quark and 2 down quarks. The question is concerned with the up quarks, right? Okay, so we want to know how many up quarks is in one atom. So we have 3 protons. So 3 times, and each proton has 2 up quarks, so 3 times 2 is going to be 6 up quarks contained in the protons, plus we have 4 neutrons, each which contain 1 up quark. So 4 times 1 is 4, so we have 6 up quarks in the protons, 4 up quarks and the neutrons, we add those together for a total of 10 up quarks. A related question to this would be one like the following, where it asks how many up and down quarks are contained in 5 helium-4 atoms. Well, here again, looking at the protons and the neutrons. The proton has 2 up and 1 down quark. The neutron has 1 up and 2 down quarks. A helium atom has 2 protons. A helium-4 would have 2 neutrons because 4 minus the 2 protons leaves 2 neutrons. So each atom, looking in terms of up and down, proton would have 2 up and 1 down, 1 up and 2 down for the neutron. So we multiply that times 2, meaning that in the proton in each atom, similar to the last question, would have 4 up and 2 down for the proton. The neutron, you'd have 2 and 4. So that would be a total of 6 up quarks and 6 down quarks for each helium atom. In this case, we have 5 helium atoms, so we would take that answer and then we would multiply that times 5, meaning that we would actually have 30 up quarks and we would have 30 down quarks.